All right, it's time to buckle up because this lesson is going to be a tough one. We're graphing rational functions. Last lesson we talked about finding the asymptotes for rational functions. We've talked throughout the year about finding x-intercepts and finding y-intercepts and how for any function, if you want to find the x-intercept, you can plug a 0 in for y. If you want to find the y-intercept, you can plug a 0 in for x. Those things still apply throughout the rest of math for the rest of your life. So we can still use those strategies along with finding asymptotes to try and graph these things. Before we get to trying to do that though, we need to try and graph them using transformations. So if you go back and review section 2.6, it was talking about graphing all sorts of different things with transformations. And remember, we had a whole bunch of parent functions like, for example, the quadratic function, y equals x squared. We had things like the absolute value function, y equals absolute value of x. We had things like the cubic function, y equals x to the third. All sorts of parent functions. We might have had 5 or 6 of them. This is another parent function that I don't think we touched on that day. The function y equals 1 over x. And this is the parent rational function, right? This is the parent function of any rational function, y equals 1 over x. This is what it looks like. And if you go back and review section 2.6, you'll remember that adding or subtracting outside of a function shifts it up or down. Adding or subtracting inside shifts it left or right. And so this minus 2 is actually going to shift this down 2. This minus 3 is actually going to shift this to the right 3. I call the minus 3 being inside because it's inside the fraction. The minus 2 being outside because it's outside the fraction. So minus outside shifting down, minus inside is shifting to the right. So if we wanted to graph this based on our parent function, we're just going to shift the whole thing, right 3, down 2, right 1, 2, 3, down 1, 2, right? And then it looks like our asymptotes are at 0 and 0 for our parent function, right? They're at 0, 0. And so now our asymptotes are just going to be shifted to those places, to the right 3 and down 2. Since our initial asymptotes were the x-axis and the y-axis, we're just shifting those right and down. Then our new function is just going to be the same shape, the same basic shape. It's going to follow those asymptotes. Remember last lesson, I made the analogy that those asymptotes are like rain gutters. They're going to catch your graph. Your graph is going to try and go towards those asymptotes, but it's not going to cross. It can, on occasion, cross the horizontal asymptote, but we would just have to check more numbers to figure out if it did, right? We would just have to check a bunch of numbers to the right and left side of the graph. In this specific graph, it's not going to. This is our g of x function. All right, if we don't have one that we can graph with transformations, this one we know we can graph with transformations because it's just a basic function. There's no x squareds anywhere, right? This is 1 over x. The only thing I've done to that function is add and subtract. And so I know I can graph it with transformations. If you have more things going on, right? So if you have a polynomial in the top and a polynomial in the bottom, like we were talking about last time, you have a true rational function, something that looks more like this, right? I've got a polynomial on top and polynomial on bottom. Then you're going to follow these rules. You're going to find the y-intercept by putting a 0 in for x. Find the x-intercept by putting a 0 in for y. We're going to find the vertical asymptotes using the rules that we did last class, and the horizontal asymptotes using the rules that we did last class. We're going to use those things to graph. We can always go back and get more points by just plugging in numbers, right? If we need more points, we feel like we need more points, then we can do that by plugging in numbers. We do want to graph at least 1 point in each interval. So if our x-intercepts and y-intercepts are not in those intervals, we want to get at least 1 point to see where it is in comparison to the horizontal asymptotes. You're going to see what that means in just a second. When I'm talking about in each interval, I'm going to describe that in more detail here in just a second. So for this function, for example, the 4 things we want to find are the x-intercepts, the y-intercept, the horizontal asymptotes, and the slant or the vertical asymptotes. For the x-intercept, if I put a 0 in for y, that'd be 0 equals x plus 3 over x minus 2. If I want to get rid of that fraction, I can multiply both sides by x minus 2 and have 0 equals x plus 3. I can subtract the 3 and get negative 3 equals x. That's my x-intercept, negative 3, 0. As long as that doesn't make the bottom 0, right? We do have to be wary of that. The y-intercept, if I put a 0 in for x, 0 plus 3 over 0 minus 2, that'd be y equals negative 3 halves, or negative 0.5. That's the same thing as the point 0, negative 3 halves, or 0, negative 1.5. X-intercept and y-intercept are done. Horizontal asymptote, remember that's the three cases. We have case 1, case 2, case 3. This one falls under case 3, where the degrees are the same. The degree of the top and bottom are the same, and so my horizontal asymptote is going to be a ratio of the coefficients, so 1 over 1. So then my horizontal asymptote is going to be y equals 1 over 1, which is the same thing as y equals 1. That's your horizontal asymptote. Vertical asymptote, we're looking for what would make the bottom 0. X cannot be 2. And is that removable? In this case, since that is not removable, then we have a vertical asymptote at x equals 2. And I'm going to go ahead and mark those in red because I'm going to graph them in red. So now when I get ready to graph this, I'm drawing my regular axis. I know that my horizontal asymptote is going to be at y equals 1. And I can draw my dashed line straight through y equals 1. I know my my vertical asymptote is going to be at x equals 2. And so I can draw my vertical asymptote in red straight through x equals 2. Now I can put on my x-intercept. So my x-intercept is at negative 3, 0, negative 1, 2, 3, 0. My y-intercept is at 0, negative 1.5. I said a minute ago that you want an x value out of each interval. And by out of each interval, I mean the separation that happens here is at 2. I have 2 points to the left. I need a point to the right, anywhere to the right of this line right here, right? I need a point to the right of my vertical asymptote. My graph is separated into two pieces. The left half, in which I do have points, and the right half where I don't have any points. So I just need to pick any x value that's out here. That would be x equals 1, 2, anything from 3 and up. Anything from 3 up. So what I'm going to do is I'm just going to go with the smallest one I can. I'm just going to pick a 3. If I put a 3 into my function, f of 3, f of 3 equals 3 plus 3 over 3 minus 2 equals 6 over 1 equals 6. That gives me the point 3, 6. I put a 3 in for x. I got a 6 out for y. So I know the point 3, 6 is on my graph. 1, 2, 3, 4, 5, 6. 3, 6. There we go. And now, looking at the separation here, I do have points to the left and to the right. I have a point in the left interval and the right interval. I need those both because I know that my graph is not going to cross that asymptote, and it's likely not going to cross this asymptote. But I do need to know whether it's above or below and left or right. I need some information on the left and the right. Now when I get ready to graph it, I'm just going to, like I said, treat those asymptotes as if they were rain gutters, right? And so to the left over here, this is going to try and run into that rain gutter. And then as it goes this way, it's going to try and run into that rain gutter. The same thing happens on the top. It may cross the horizontal one, but even if it does, it's going to try and come back to that rain gutter. It's going to go up to that rain gutter. Water flows down here, flows into that rain gutter. It does not want to cross those red lines. All right, let's try another one. 4x over x squared minus 4. The same four things that we want. We want the x-intercepts. We want the y-intercepts. We want the horizontal asymptotes and the vertical asymptotes. For x-intercepts, if I put a 0 in for y, 0 equals 4x over x squared minus 4. I can multiply both sides by x squared minus 4 and have 0 equals 4x. Divide both sides by 4 and have 0 equals x. So that's 0.00. If 0, 0 is your x-intercept, it must also be your y-intercept since both things are 0. But we can check it anyways. If I said y equals 4 times 0 over 0 squared minus 4, that'd be 0 over negative 4, which is 0. So that's the point 0, 0. Our x-intercept and our y-intercept are 0, 0. Horizontal asymptote, this is case 2, where the bottom has higher degree. And so our horizontal asymptote is at y equals 0. Our vertical asymptote, we're looking for things that make the bottom 0. This is actually the same as 4x over x minus 2, x plus 2. Really helps to know those factoring rules. So then x cannot equal 2 and x cannot equal negative 2. Are either of those removable? And it happens that they are not. Neither of them are removable. So we have two vertical asymptotes at x equals 2 and at x equals negative 2. Our graph absolutely cannot cross those lines. All right, we have a horizontal asymptote. I'm going to do the asymptotes first. Horizontal asymptote at y equals 0. Remember, this one is flexible. It can cross it, but it's going to want to follow that rain gutter. Vertical asymptote at x equals negative 2. Vertical asymptote at x equals positive 2. And I only have 1 point here. So I'm going to have to find quite a few more points to be able to fill this graph out and figure out what happens, especially since that point lands directly on that asymptote. If it lands directly on it, it's going to have to cross it, right? And so I'm really going to have to get a bunch of points to try and figure out what's going on, especially in that middle region where it lands on the asymptote, because that's a little funny. I'm going to make a t-chart and see if I can't figure some numbers out. So in the left region, that would be something like at negative 1, 2, 3, negative 3. In the right region would be something like positive 3. In the middle region, it would really help to have negative 1 and positive 1. That would give me a better idea of what was going on. I'm going to use my calculator here and sub in these values. So negative 3, and I'm typing in my calculator, parentheses, 4 times 3 divided by parentheses negative 3 squared minus 4. And I get negative 2.4. If I do a positive 3, I get positive 2.4. If I do a negative 1, then I get negative 1.3. And if I do a positive 1, I get a negative 1.3. I think I did one of these wrong. I need to type those back in real quick. Positive 1, negative 1, negative 1. I get a positive 1.3. Okay, I knew that looked a little fishy. Let's put those points on the graph and see what that means. Negative 1, positive 1.3. Positive 1, negative 1.3. So in this middle region, it looks like if it follows this rain gutter and follows this rain gutter, it's going to end up looking a little bit like one of those cubic functions. Negative 3, negative 2.4 is out here. I could even do, if I wanted to, I could get more information with negative 4 and positive 4. And that's going to give me something like this, right? Where it's going to follow those rain gutters. And at positive 3, I had positive 2.4, which is up here. And again, if I plugged in a positive 4, I'm going to get something down here. And it's going to follow that rain gutter. And that's what my graph is going to look like. That was a lot of work for this graph. Like I said, hold on tight because we have a lot more to go. I am going to give you a chance to try some of these out. I think it's going to help for you to actually look at these on your own and look at the pieces and see what they mean. Here's one where I'm going to let you try on your own. Take a second and see what you can do. I'm going to unfreeze in 5 seconds. Here's the information that I found on this graph. The vertical asymptotes, there are none because there's no way to make the bottom 0. The horizontal asymptote is at y equals 2 because they have the same degree. That's case 3. So we just take the ratio of the coefficients 2 over 1, which makes y equals 2. The x-intercepts, we set the whole thing equal to 0, multiply by x squared plus 1. The top we can factor and find that 5 halves and positive 1 are your x-intercepts. The y-intercepts, when you sub a 0 in for x on top and bottom, you just get negative 5. I've tried to color coordinate this where the y-intercept is that yellow color, the x-intercepts are that purple color, the asymptotes are in red. And since it does not want to pass through those asymptotes, which it very well may, it very well could end up passing like this, just over it and across, or just over it and across on either one of these sides. Because a horizontal asymptote is a little more flexible, right? A vertical asymptote, it will never cross. A horizontal asymptote, it could cross. So what I'm saying here is, I have this following that line, but it could happen that it crosses on both sides, honestly. But it's going to still follow. It's going to still follow that asymptote. Let's say it crossed over there, right? Or it could do vice versa. It could say it crossed over here. We would really have to get some more points to figure that out. Here's what we could do. If we wanted to know whether it crossed it, we could pick a number way off to the left. So we could do a t-chart and say a number way off to the left would be like negative 20. A number way off to the right would be like positive 20 or positive 100 or something. And we could plug those numbers in. So if I plugged a negative 20 in, and I would say 2 parentheses, 2 times negative 20 squared minus 3 times negative 20 minus 5, close parentheses, divided by parentheses, negative 20 squared plus 1. And I do get 2.13, which is over 2. Remember, this asymptote is at 2, so I know that it crosses it on this side. Let's plug in a positive 20. Positive 20 into the same exact function. I get 1.83. And so it probably does not cross it on the right. Actually, I know it doesn't cross it on the right because that's still below 2. And so it is the case, what I was saying earlier is true, that it actually does cross this asymptote. This is the first example that we've had where it does cross it. And so we know it stays below it on the right because at positive 20 it's still below 2, right? But on the left, since it's actually above it at 2.8, it actually goes above it and tries to chase that asymptote on that side. I hope that one gave you a little bit of confidence. If not, you're going to have plenty more opportunities. That's the third one that we've graphed. We're going to graph several more. Here's another example. Let's try and find all those things. For all of these, I would suggest pausing, finding all the stuff that you can, and then catching back up with me. The x-intercept, if I plugged a 0 in for y, and I know I'm going to end up multiplying by this to get rid of it, and so I'm going to have 2x squared plus 9x plus 4, and then I can factor that as 2x plus 1, x plus 4, and so my x-intercepts are at negative 1/2, negative 4. That's negative 1/2, 0, negative 4, 0. The y-intercepts, if I plugged in 0 for x, that'd be y equals 2 times 0 squared plus 9 times 0 plus 4 over 0 plus 3. I plug that in the calculator and I get 4 over 3. So that'd be the point 0, 4 over 3. My horizontal asymptotes. This looks like it's case 1, where there is no horizontal asymptotes. In fact, I said earlier that it's a slant asymptote, but we're not going to be able to find that. You could find it. There is a way to find it, but we're not going to find it. Vertical asymptote, we're looking for what would make the bottom 0 that's not removable, and that x equals 3, x equals -3 would make the bottom 0, and even if I factored the top, it would not be removed. And so I'm going to graph these in red. I'm going to graph this in yellow. I'll graph these in this purple color, and we'll see what happens here. So we have the point -1, 2, 3, 4, 0. The point -1/2, 0. The point 0, 4 over 3, which is like 1.33. And we have a vertical asymptote at x equals -3, so it's not going to cross that line right there. And I do have something in every region, but it would be helpful if I had a little bit more in that left region. At least in the right region, I have 2 points, and I can tell if it chases that it's going to be going that way, right? On the left side, it'd be nice to have one more point. So if I do my XYT chart, I'm just going to plug in. That's at -4. The furthest left point I have here is at -4. So I'm going to try -7, right? And I'm just going to sub that in my calculator. So that'd be 2 times -7 squared plus 9 times -7 plus 4 all over -7 plus 3. And I get -9.75. So at -4, 5, 6, 7, I'm way down here negative. And so it looks like this one, if we want it to go towards that vertical asymptote, right? We want it to go towards the gutter. It's actually going towards the gutter in this way. It's going to run into the gutter that way. It's not going to run into a vertical asymptote on both ends, right? So it's not going to loop and come back around, because that wouldn't be a function. It wouldn't pass the vertical line test. This thing does still have to pass the vertical line test. So there's no way, if I have to connect these 2 points and it has to go towards that red dashed line, I can't go towards the red dashed line on this side, or else I'm not passing that function test. It has to go towards the red line on this side, and this side must be going outwards. You could write out the limits here. We talked about as x approaches -3 from the right, f of x, look at this, as it approaches -3 from the right, f of x is going downwards, so towards -infinity. You could do the same thing from the left. From the left, it's approaching positive infinity. All right, take a second to try this one out. I'm going to unfreeze it in 5 seconds. This is what you got. Vertical asymptotes, horizontal asymptotes, your points. I subbed in a -4 just to get one extra point here to see what it looks like. So if you subbed in a -4, you get -10.5, which is somewhere way down here, way on down here. And so the same thing, we want this to maintain its function shape. We don't want to have any vertical line test issues. And so the function has to look something like that. Very similar to our last one. All right, the next ones are going to be more reminiscent of what you would see on a test or a quiz, right? This is something that you definitely could see on a quiz. Let's try this one again. I would pause it, see if you can do it. To find the x-intercepts, y-intercepts. So finding the x-intercept, we know the bottom we're going to get rid of, 2x minus 4. So our x-intercept is 2, 0. Our y-intercept is -4 over 3. Our horizontal asymptote, this is another case 3, where they have the same degree, and so we're going to look at the ratio of their coefficients, 2 over 1. So y equals 2 over 1, or y equals 2. Vertical asymptotes, -3 would make the bottom 0, and it's not going to be removable. Let's see if we can graph this. This should be a much easier one to graph. At y equals 1, 2, we have a horizontal asymptote. At x equals -3, we have a vertical asymptote. We have points at 2, 0. We have another point at 0, negative 4 over 3, which is 0, negative 1 and a third. And so our right side of the graph is filled out nicely. We have nothing on the left side of the graph, so we are going to have to sub in a point, maybe negative 4. We just need to see if it's above or below that line, really. And so what we could do is, at negative 4, f of negative 4, when we sub a negative 4 in, 2 times negative 4 minus 4 divided by negative 4 plus 3. I get a 12, which is way up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, sure. It's above, and so we know it's going to chase that. It's going to chase that asymptote as well. And so that is our graph of our function. Like I said, this is more of a typical rational function. This is what a typical rational function looks like, if you could call any of them typical. Slide 10 of 12, we're almost there. 2 more slides. Take a second, pause, and see if you can do this one. X-intercepts. 0 equals 4. There's no way to do that. No x-intercepts. There's no way to make the top 0. For x-intercepts, what you're essentially doing is trying to make the top 0, right? Where for vertical asymptotes, you're trying to make the bottom 0. For x-intercepts, you're trying to make the top 0. For y-intercepts, if we plug a 0 in for x, y equals 4 over 0 squared minus 16. That'd be y equals negative 1/4. That's 0, negative 1 over 4. Horizontal asymptote, this is a case 2. So y equals 0. And for vertical asymptotes, you're going to have positive 4 or negative 4 will make the bottom 0. Neither of those are removable. The reason I know that, this is 4 over x plus 4, x minus 4 when you factor it. So 4 and negative 4 would make the bottom 0. There's nothing I can get rid of, nothing that matches up perfectly from top to bottom. So again, I'm going to graph my asymptotes in red. Y equals 0. X equals negative 4. My x-intercept is not anywhere. We don't have an x-intercept, which makes a little bit of sense because we do have that asymptote there. If we had an x-intercept and a y-asymptote at 0, then it would have to cross that asymptote. It might look a little goofy. We do have a y-asymptote at 0, negative 1/4, which is over here. This one I think is going to be helpful to get a couple more points. X, y. If we sub in maybe a negative 2 for x, if we sub in a negative 4 for x, so I'm looking here, I'm looking here. Just to get some ideas of what's going on, whether it's going to stay above or below. I have a feeling at negative 2 it's going to be down here somewhere, but we'll find out. If you sub in a negative 2, that'd be 4 over negative 2 squared minus 16 is negative 1/3. So yeah, it is. It's still down here somewhere. And so on the right side, it is going to follow that asymptote and then chase that asymptote downwards. To the left, if I sub in a negative 4, that'd be 4 over negative 4. Oh, wait. I have messed up here. I have 2 asymptotes. I'm not even looking at both of them. X equals 4 and x equals negative 4. I need to erase some of this work now. I've messed up. X equals 1, 2, 3, 4. 1, 2, 3, 4. And so we have a vertical asymptote here as well. Since this thing's looking a little bit symmetric, that blue dash is below the x-axis. I'm willing to bet that if we plugged in a positive 2, it would also be, what did I get here? Let's see, 4 over 2 squared minus 16. I got negative 1/3. And if I plugged in a positive 2, I also got the same thing. Positive 2, I got negative 1/3. And so this is very symmetric on this middle portion. It's going to sort of chase all 3 of those. So now I need something out to the extra wings, maybe a negative 5 and a positive 5 to see. I bet those are above this axis. Typically, they do flip-flop. So if I plug in a 5 and a negative 5, 4 over 5 squared minus 16. That's 0.4. And if I do negative 5 squared plus 16, I also get 0.4. And so this is above the axis, not quite to 1. This is above the axis, not quite to 1. I could plug in more numbers if I wanted to, but I think I've got a good enough idea of what's happening here. This is going to follow those. This one's going to follow those. And that's what my rational equation looks like. That's what my rational function looks like. All right, I believe we only have one more. This is another one you should definitely try. Pause it. I'm going to count to 5, and then I'm going to unhide it. This is all your work here. You've got vertical asymptote, you've got a horizontal asymptote, you've got an x-intercept. Actually, you don't have an x-intercept. There's no way to make the top 0. You have a y-intercept at negative 3 over 7. I've got that plotted in yellow. These 2 points, negative 3, negative 3, negative 1, 2, 3, negative 1, 2, 3. That's down here. That's that point right there. And the point negative 5, positive 1 is up here. So my graph should look something like that. I could do more points. I could do even more points if I wanted to get a better idea of where this graph was going. But I think that's enough. I have the experience to look at it and sort of see where it's going. Until you get there, I absolutely would make a t-chart, right? And just do as many numbers as you can. So you know you have the number 0, negative 3 sevenths, because that's your y-intercept. You know you have the point negative 3, negative 3. You know you have the point negative 5, 1. I might plug in also to get a better idea, negative 7. I might plug in negative 2, and just get some of those points on this graph that are going to help you get a better idea of what this graph looks like. Maybe negative 4 would be a good one. Negative 4 would be a good one to plug in. It's going to be up here somewhere. But that's the idea behind rational functions. The things you really want, the pieces of information you really want are the x-intercept, the y-intercept, the horizontal asymptotes, the vertical asymptotes, and then any extra points that you feel like you'll need.